let's look at the concept of virtual work. Basically, when it comes to virtual work, there are four key things we're going to be looking at. We're looking at energy method for computing deflection. We'll look at principle of virtual work, also virtual work in terms of trusses. I'll look at the procedure in solving problems under virtual work. When it comes to virtual work, there we have virtual work for trusses and virtual work for beams, right? And when it comes to virtual work for trusses, which is which we're going to be doing right now, there are three formulas there, right? We have the equation for virtual work in terms of trusses, and also we have equation of virtual work in terms of trusses, but what in terms of what temperature. We also have fabrication error in terms of virtual work trusses. These are like three formulas we have under virtual work trusses. So I said we have virtual work equation itself in terms of trusses. We also have virtual work equation in terms of change in temperature, right? When temperature occur, we have the formula we use for virtual work in terms of trusses. Also, we have the formula of virtual work in terms of trusses when there is what a fabrication error. We have the formula we use there. So let's look at this one after the other. Let's have the first one called the energy method for computing deflection. When it comes to energy method for computing deflection, here is what you need to note, please. Basically, for this one here, energy method are based on the principle of conservation of energy, right? So note that energy method of computing deflection are based on principle of conversion of energy. What's the principle of conversion of energy? The principle of conversion of energy is that UE is equal to what the UI. This is UE is refers to work done by all external forces. So UE is refers to as work done by all external forces. While UE is work done by all external forces, while UI is called the internal forces, internal work done per se, internal work done, or per internal work if you want to. Work done and work are still the same thing. Internal work into a bracket, strain energy stored in the structure. So note that when it comes to energy method of computing deflection, we said these are based on conservation of energy, and from the concept of conservation of energy, we said UE is equal to what? UI. What's UE? Work done by all external forces. UI, internal work done, that is strain energy stored in a structure. So I have this introduction for energy method for computing deflection. Basically, let's start with the first one here called work done by all external forces, UE. Let's consider UE. Let's consider external forces, external work done per se, external work done due to external work done. Let me call it UE per se. Let's consider this first one called external work done, that is UE. Basically, mathematically, we express UE, which is external work done, as being equal to the integral of x0 f dx. So note that initially work done is meant to be force times distance, perpendicular distance. In this case here, my distance is dx, my force is tf. So I'm going to introduce a definite integral of upper limit x, lower limit 0 f dx. So when I'm trying to calculate for external work done. The formula is given as the integral of x to lower limit 0 f dx. Now listen up. In terms of elastic structure, UE is equal to P change over 2. So notice please, when in terms of just a normal external work done is said to be integral of x 0 f dx. But when it comes to elastic structure, the formula becomes P delta over 2. This becomes your mathematical expression for external work done. All right, let's look at second one called the internal work done. Internal work. For this one here, that's UI. So listen up, please. Listen up, please. We said this UI. Listen up. Let's write the formula, please. Basically, the formula should be UI is equal to UI per se is equal to half. All right, half n into, that is small n into NL over AE. This is the expression for UI, right? So let's see if you can get this expression there. Yeah, I'm correct. That's it there. So let's see if you can derive this. Let's derive this formula, please. When it comes to internal work, we said strain energy stored in a structure. Now that will lead us to our concept of state of material, right? From here, now look up, please. From here, UI is initially half times n times delta. See this symbol? Either I use this symbol or I use change in L. They are the same thing. So either I use this symbol or I use this, they are the same thing. So per se, I can use change in L. Look up, please. All right. Look up, please. So these two are say the same thing. So this is change in L or delta. If you want to, anyone if you want to, they say the same thing, please. Basically, 1/2 is constant, n is constant, but I can derive the expression for delta. This one here. Go back to your normal initial concept of state of material, right? Go to your normal physics concept. From here, we said stress. Recall from here. Recall that stress, that is sigma. Stress is a Greek symbol, sigma. So stress is what? Force over area, as we said in the last class, like initial last class of physics. You should know this. Also recall that strain, that is epsilon, is what? Change in L over what? Original length. All right. So I can use this symbol to represent change in L, right, over original length. I have this one here. Now, again, also recall from your Young's modulus that Young's modulus E is equal to what? Stress over strain. This is E signifies modulus of elasticity is equal to what? Stress over strain. From here, E is now equal to what is stress? Stress, of course, FA. So I have F over A for your stress, all over what's your per se strain, delta over L. So I have delta over L. So I have these symbols here. From here now, I'll do some manipulation and so we get. Doing manipulation from here, I'll have that E, which is modulus of elasticity. Keep this one down. That's F over A. This one is this. This symbol is divided by, this is delta over what? Over L. From here, I'll have that E is equal to F over A times, change this division to times. This L comes first over delta, yeah? Combine these four together, E now is equal to FL over A delta. Now from here, I'll make delta subject. How? Swap the position. This delta, put it here. This E, put it here. So I'm saying that delta now will be equal to FL over A capital E. Observe, please. I said swap position. This one should come here. This one should go here. So this delta should come here. This E should go here. I'll have this, right? Now we said that UI initially was half times what? N, small n, please, times small n, times small n, times what? Delta, delta. From here now, ui, which is referred to as internal work, is equal to half times n times, what's your delta, is what? FL over what? AE. Basically, our F, I can express F as being capital N, please. They are the same thing, please. So I can put my F as capital N. So for me, I will have F now is capital N. So I have capital N L all over A E. So this becomes my mathematical expression for UI. So I'm saying that UI is equal to what? Is equal to 1 over 2 n capital N L over A E. This becomes my mathematical expression for internal work. So I have this one here as my expression for internal work. So we're done with the derivation. Let's look at, that's your first task. So we are done with the first concept there, called the energy method of computing deflection. So we have the internal energy method, and we have the external, sorry, we have the work done by external force, and we also have the internal work, right? When it comes to energy method for computing deflection, there are two. The first one is what? UE. Second one is what? UI. And I've given you the expression here. All right, let's look at the principle of virtual work. Very important, please. A very important concept. The principle of virtual work, please. Let's look at yet the principle of virtual work. Let's look at the principle of virtual work. A quick introduction, our hope, please. The principle of virtual work is based on the conservation of energy and was developed by John Bernoulli, right, in 1717, also called unit load method. So when it comes to principle of virtual work, I'm actually working with the concept of unit load method. So in this course generally, whenever you are given any diagram, that diagram you are given is referred to as a real diagram. Are you there? So that diagram you are given is referred to as a real diagram. You must always draw out the virtual work, or perhaps virtual diagram. What's virtual? Virtual is like an imagination, right? Imagination, not a real diagram, but what? An imagination diagram. So when you're given a diagram, for instance, when you're given a question, like a question in an exam, your first time is that question is the real diagram. You will now mask out that same diagram, but in this case now, you will be drawing what? The virtual diagram, right? So I'm saying that virtual diagram now is refers to, is also called unit load method, please. Principle of virtual work is also refers to as unit load method. So your ability to convert real diagram to virtual, which is imaginary. So in this case now, let's say I have a real diagram. Let's say I have something of this nature. Observe. Let's say I have something of this nature. I have here as 4 kilonewton, right? So I have something of this nature. From here to here. Here is 4 meters, 4 meters. This is A, this is B, this is C. Let's say I have this structure here. This one is a real diagram. This is a real structure. To solve this problem now, you have to draw out your virtual diagram. So for the virtual diagram, I'll still have the same thing here, but basically, this is my original force. So we called virtual work as what? A unit load method. So the task is that any load I'm seeing from the real diagram, I'll convert it to what? A unit load. In science, when you say something is unity is 1. So I'll convert this one to what? A 1. That becomes what? A point load, 1 kilonewton. I'll convert this original force. That's all. Now draw the diagram back. I have this 4 meters B C A, right? I have pin here and ruler. So your ability to convert read diagram to unit load method is the concept of virtual work. So just convert the original force given to what? Just one unit load method. Unit means one. Convert it to one. That's the place. So I have this. This is like the basic explanation for unit load method principle per se. So I don't want to stress myself too much. I just try to use this diagram to explain. When it comes to virtual work, I am converting the real diagram to a virtual, to imaginary. So any force you are given, ensure that you take it to what? You convert it to one. It becomes one here. This is the real diagram, no problem. This is a virtual diagram here. Convert the original diagram to just one. That's the concept, please. That's the principle behind virtual work. All right, let's look at the second concept there called virtual work trusses, please. See, this one here is very important. Let's look at the concept of virtual work trusses, please. Virtual work per se trusses, please. Trusses. For virtual work trusses, please. Listen up, please. Virtual work trusses, please look up. When it comes to virtual work trusses, there are three mathematical expressions there I'll give you. So go and memorize the formulas. There are three formulas there, please. So I'm saying that when it comes to virtual work trusses, there are three expressions there. Now listen up, please. When it comes to this same concept of virtual work trusses, where there are three expressions there, the first one is refers to as virtual force equation, right? So the first one there is called the virtual force equation. Please mind you, this is virtual work equation under what? Under trusses. We still have virtual work equation under what? Under beam. This is trusses, please. This is trusses. So for me now, I have virtual force equation under what? Under trusses. The formula is given by 1 dot delta is equal to summation of n into nl over ae. This becomes your mathematical expression for calculating virtual force equation when it comes to trusses. I have this. Keep on pending. This is my first equation there. The second equation, look up, please. The second equation, I want to make this course. I want to make it quickly and we'll round it up, please. This is the first equation there. The second equation under virtual work force trusses is when you have a change in temperature. There's no how in real life sense, if you have a trusses or perhaps let me say a bridge, for instance, a bridge, when heat is applied to a bridge, we know that from idea of physics, it expands. So when the bridge or perhaps when heat is applied to a virtual work trusses, it tends to what? Expand. When it expands, listen up, please. When it expands, the expression now changes. It's not this one again. So when it comes to temperature change, virtual work done, that is so it's given by 1 dot change is equal to what? Summation n dot alpha change in TL. Please know this, please. Very important. Note that when it comes to temperature concept under virtual work trusses, so I'm saying that there are just three expressions or perhaps three formulas for virtual work for trusses. We said the first one is what? The real virtual work is equation. I have this. The second one there is called the temperature change, right? So when you have a temperature change, when it comes to trusses, you apply this formula. Also, there's what we called fabricational error. That is, when there's error in the trusses, right, becomes a fabricational error, you apply this expression. So when it comes to that temperature change, when you have a trusses outside, because you can't build a trusses in your room, is a structure, is a open space structure. So when when it's afternoon, when sun is heated, when sun applies its temperature to the trusses, it tends to what expand, right? So that's why we have what we call the temperature change. So when it comes to trusses, there, virtual work trusses, we have temperature change formula, and we have the fabrication of area. At this point now, I can combine all the virtual work trusses equation together by saying in general, the virtual work forces equation becomes one dot change is equal to what? Summation n into nl over ae. This is for my normal equation there, plus summation n dot alpha L change in T, my temperature there. Finally, I have plus summation n dot change in L. This is for what? This is for my, this last one here is for this one here, fabrication error. So note this formula, very, very important when it comes to the concept of virtual work. In terms of trusses, please, I have this. These are trusses expression, please. I have this. So I have this one here. Let's look at yet on that concept. Basically, before my camera was went off, so I had to um do this place again. So I explained something earlier before the camera went off. I said kilo is 10 to the power 3, mega 10 to the power 6, giga 10 to the power 9, tera 10 to the power 12. Very important things to note. So let's say I have 20 gigapascal, for instance. 20 is this 20 here. Giga, I told you that giga 9 is 10 to the power 9, 10 to the power 9. Pascal is equal to, so not that 1 pascal is equal to what? 1 kilonewton per meter squared. So if I have pascal, it signifies what? Kilonewton per meter squared signifies pascal. So I have converted pascal, gigapascal to what? Kilonewton per meter squared. So you have to convert this stuff here. All right, let's look at virtual work in terms of what? Beam. So I said I'll show you the procedure to virtual work in terms of trusses in the screen in front of you. All right, let's look at virtual work in terms of beam, right?